Okay. Hey, so guys, I'm going to invite you to join me at the calendar here just really quickly. So guys, there are some major changes to the end of the month, and therefore the end of the quarter. And guys, if you're paying attention when you first hear this, this may cause you some concern. But guys, what I want to do is I want to explain to you the reasoning behind this, and then also reassure you that Miss Call and I will never set you up for failure. But guys, it goes like this. You may remember that as we were talking about the end of the quarter, we talked about the idea that Miss Call and I compressed the unit that we're currently involved in simply to get the test done before Christmas, thinking that that's better for you, because if you have to remember stuff after Christmas, that's going to be a mess because you're going to forget everything over Christmas break. But then, guys, Miss Call and I sat down and we started to talk about it, and we realized kind of quickly that we were doing more harm than good by hurrying. Guys, you're going to see that the material that you're going to learn starting today is going to be fundamental to what we do basically for the next 2 months. And we started to think about this, and we're like, wait a minute. So we're expecting them to learn it on Tuesday so well that they have it nailed down on Thursday so that we can go even deeper on Thursday so that we can then use it in lab on Monday so that then they can do well on the test on Wednesday. And guys, experience told us that that is completely inappropriate. So what we decided to do is just slow way down. So guys, understand that relative to the end of the quarter, this will not only change the way the quarter is going to end, it's also going to change the things that apply to your second quarter grade. So I want to talk with you about this. So guys, fundamentally what we did is we brought back everything that should have been part of this unit. And this then is what that looks like. Guys, today on Tuesday the 7th, we are going to go over what are called Lewis dot molecular structures. In the previous unit, you did Lewis dot atomic structures. Today, we're going to do these for molecules. But guys, this is a huge thing that you've got to understand. Guys, it's so huge that every year we give people a whole nother day on Thursday to get this figured out. Guys, this was one of the things that we initially got rid of, and we're like, that's not okay. So guys, here's the way this is going to go. You're going to learn this today. We're going to grade that homework on Thursday, and then guys, there will be no instruction on Thursday. You're just going to have the entire day to really dial this skill in so that you're really good at it. So guys, this is one of the few things during the year that we will spend 2 days on. It's that important. Then guys, when we come back on Monday, we're going to drill into that idea a little bit more deeply. You'll see. Then guys, when I see you on Wednesday the 15th, this will be the last academic day of the quarter. And guys, we're actually going to be working on an activity that will go on your third quarter grade. So again, guys, we're just bringing back the stuff that we would have skipped. So you'll notice then, guys, that the test is now after Christmas. So you're going, wait a minute, you told us that was bad and now you're doing this to us. Well, guys, remember the test would have gone on your third quarter grade anyway, but I want to show you how this is going to go. What's going to happen is when we get back after Christmas break, we're going to come back immediately to a lab. And guys, this lab is actually the last 2 pages of the test, the stuff that I'm afraid that you would have forgotten. And so guys, understand, you're not going to come back to a test. You're going to come back to a huge test review. And guys, you're going to see by the end of this, you're going to be completely back up to speed, and then you'll be all set for the test on Thursday. So guys, it would have been a huge mistake to give you the test on Tuesday, but you just got to trust me on this. This lab is going to get you completely caught up with the stuff that you're learning now, and then you guys will be just fine for the test on Thursday. So guys, here's then what that means to your grade. There's one more homework assignment on your second quarter grade. We added back that additional second day of practice, so that will be on your grade. And then there's one fewer labs on your grade, because this lab was going to be on your second quarter grade, but now we're doing it after Christmas, which means that it is no longer on your second quarter grade. So guys, functionally then, here's what that means. Let me show you. And I know you guys can see this, but this is worth doing. Guys, this then is what that means. Here's skyward, and so what you're going to notice is that the test column is all filled up. And I know you can't see this other than to see that there are numbers in all the test scores. Guys, we're done with tests. Remember, today is the last day for remediation. If you qualified for remediation, you need to watch the video and done the homework assignment. It's in here, 155, last chance, today after school. And then guys, you'll notice that labs, we have one column with asterisks. That is the lab that you should have turned in this morning. And then guys, finally, you'll notice that you've got 3 now homework assignments left instead of 2. So this then defines the rest of the quarter. If you're good on the test and you're not doing remediation, and if you just turned in the lab, the only things that you have left for this quarter are those 3 homework assignments, and that's the end of the quarter for you. Okay, so guys, any thoughts, any concerns, any questions about any of this? You guys okay? Okay, so guys, with that said, you need a periodic table. You need something to take notes on. Get this out of the way, and here we go. Put this away. Actually, not quite yet. Do this, do this, do this, do this, and this, and this, and this, and good. All right. All right, so guys, here's the $11,000 question as you're getting settled. What on earth could be so important that Miss Call and I decided to completely redo the schedule for the rest of the calendar year and spend 2 days on something? And guys, if you think about this, this has never happened before, and it will only happen one more time in February. Guys, what is so important that this warrants completely rewriting our schedule at Christmas and spending an additional day on it? And guys, the answer is this: Lewis dot molecular structures. So guys, what is so important about Lewis dot molecular structures that it warrants all of this time and attention? Well, guys, you're going to get a little sense of it today. But what you're going to see, you won't really be able to fully appreciate this till we get back after Christmas. So right now, you're just going to have to trust me. These are important. But guys, let me tell you up front, this is not a concept. This is a skill. And guys, you know the difference in this class. This is not a concept, this is a skill. So we're going to handle this differently. I'm going to encourage you to be very conservative in terms of the notes that you take. I will tell you when something is worth writing down. But guys, you're going to see that quickly we're going to stop talking about ideas and we're going to start doing stuff. And I'm going to do 4 examples of these for you so that you have some examples to work off of. And then guys, at that point, you're just going to practice. So guys, do not write anything down other than this until I tell you. So guys, let me help you catch up with where we are. So guys, joining me at the screen, this looks familiar because this is the last thing you did with the screencast on Friday. And so guys, we talked about ionic, we talked about covalent, we talked about metallic bonding, we talked about salts and molecules, and we talked about metals. Well guys, here's the deal. We are now done with ionic bonding. Ionic bonding leads to salts, and we're done with that. Guys, we are also done with metallic bonding. Metallic bonding leads to the sea of electrons. And guys, we are now done with this and that. So guys, the only thing that we have left, and this is where we're going to spend the rest of this unit, is covalent bonding, and that leads to molecules. So guys, put the ideas together. Lewis dot molecular structures. See the connection? So guys, what we're going to do today is we're going to talk about how do we represent molecules. So in order to do that, and that's molecules under there, guys, we need to do a quick review. Don't write any of this down, but you should know the answers to these questions. So guys, when we talk about molecules, we're talking about sharing of electrons, covalent bonds. And guys, we're going to be drawing Lewis dot structures, so we need to remind ourselves about Lewis dot structures. So guys, don't even write down the answers, but you should know them. Guys, which are the electrons that appear in Lewis dot structures? The valence electrons. They are the ones on the outside. How many dots can there be? 8, up to 8. That's why biology teachers lied to you and said 2, 8, 8, 8, 8. Because all biology teachers care about are valence electrons. Now guys, which sublevels are these valence electrons in? The highest? S or P, never D's and F's. So guys, these are in the highest S and P. Now guys, how many electrons can be in the S? How many electrons are in the S? 2. How many are in the P? The other 6. And so guys, this then leads us to where we need to go with this. So guys, how many orbitals do these occupy? Well, there's one box, the spherical S. Let's go over to Max's beautiful representation. So guys, we remember that the S orbital is the one sphere, and then the P orbitals are these amazing 3 dumbbell-shaped spaces. So guys, there's one S and there's 3 P orbitals. Is all of this good? Okay. This then, guys, leads us to something you need to include in your notes. Guys, this then leads us to a driving principle that we are going to use in order to draw Lewis dot structures. Please write this down with me. It is called the Octet Rule. But guys, this should come as no surprise. Oct is 8. So it's a rule about 8. But there can only be 8 valence electrons. So guys, this is really straightforward. The Octet Rule says this. When atoms bond, they are most stable when they have a complete shell of 8 valence electrons. And guys, this is going to be important to us throughout the day, throughout the week, throughout the quarter, throughout the year. So, Octet Rule, driving principle, simply says 8 electrons. All right. So guys, what we're going to do now that we've laid the foundational framework for this is we're going to start doing stuff. We're going to start with stuff you should know. Then we're going to move into stuff that is putting literally the pieces together. So guys, one of the essentials on the last test was Lewis dot structures. So you should, are y'all caught up? Guys, you should be able to do this. Please draw in your notes and spread them out like this. Give yourself a little space. So guys, skip down like 2 or 3 lines. And across the first line, you will write down then hydrogen, nitrogen, and oxygen. Then skip down 3 more lines, and then chlorine and carbon. And guys, what you need to do is you need to draw the Lewis dot structures for these 5 elements. Now guys, here's the deal. If you can't do this, I'm really hoping that you're doing remediation. Because guys, Lewis dot structures don't go away. You've got to be able to do these. So if you can't, this is going to be something you're going to have to address relatively quickly. But guys, if you're sitting there and you're going, wait a minute, I know how to draw Lewis dot structures. This is a waste of my time. This is not a waste of your time. Because guys, we're going to use these Lewis dot structures as a foundation for what you're going to learn today. So you're going to find that it is in fact worth your time to draw these. There's an idea lurking in these Lewis dot structures that you're only really going to get if you draw these. Now guys, understand if you can't draw these, you understand that that's a gap you're going to have to fill. Remediation is a great way to do that. But guys, if you can't do these, I'm going to encourage you, frankly, to just copy my answers so that you have them. So I'll give you another second to do these, and then we'll gather this all together. All right, are you guys caught up? You're okay? I'll give you another second. How about now? Yeah?
This is confusing, but is the second letter in some of the
abbreviations?
Lowercase?
It's always lowercase. Yeah, so if you've got a second letter in the abbreviation, it has to be lowercase. Yes, you want to do them properly. There's actually a reason why, and we'll talk about it after Christmas. Okay, so guys, why am I asking you to draw Lewis dot structures if these are something that you should be able to do? And the answer is this. So guys, hydrogen has got one dot. If you didn't know that, join me and write it down. But guys, this is the new idea that you need to become aware of. It's the idea of what are called bonding sites. I would encourage you to write this in hydrogen as a way of reminding yourself what they are. So guys, this is a bonding site. We're representing it right now with a box, but here's what a bonding site is. It is an orbital that has one but not two electrons. So guys, we've already established that that electron is in the s orbital. It's the first electron. Doesn't matter if it's top, bottom, left, or right. The trick is that it's alone. And so guys, hydrogen has got one bonding site because it's got one electron by itself. Notice that it doesn't have 7 bonding sites. It has to be 1 but not 2. Empty orbitals do not create bonds. So these are not available for bonding. It's 1 but not 2. So now guys, turn your attention to nitrogen. If you didn't know that it's got 5 valence electrons spread out like this, please write it down. But now guys, I've got a question for you. How many bonding sites does nitrogen have? 3. You see them? They're right here. 1 and 2 and 3 bonding sites. Gracie, go ahead. It doesn't at all. So this is what, and this is what eventually makes this unit a little bit trickier, is that these are not accurate 3-dimensional anyway. Atoms are not flat, these are spheres, so these electrons are not 90 degrees to each other anyway. So up and down and left and right don't matter. We're going to get even deeper into that next week, but for now it doesn't matter. So guys, you good on this idea of 3 bonding sites? So now turn your attention to oxygen. Guys, oxygen has got 6 valence electrons. How many bonding sites? You starting to get the idea? You feeling okay about bonding sites? Then guys, looking at chlorine. Chlorine, and again, if you didn't know this, please write it down. Chlorine's got 7 valence electrons. How many bonding sites? 1. But now guys, watch this. And well, just check this out. So guys, carbon. Good. So guys, carbon only has 2 bonding sites. But guys, here's the deal. Watch. We are not going to handle it that way. So David, I think that was you that said 2. And you're right. There's a bonding site here and there's a bonding site there. And that's true, except for this. Guys, when carbon forms bonds, all of its electrons actually spread out. And when they do, they turn into this. And when that happens, how many bonding sites does carbon now have? 4. So guys, this is an important idea, and I'm going to ask you to go back and do this, please. So guys, we have this new idea that says when atoms form bonds, their electrons spread out. And so carbon's electrons spread out. So instead of having 2 bonding sites, it's got 4 bonding sites. But guys, here's the trick. Carbon is not the only element that does that. All of these atoms do that. So guys, here's what I need you to do really quickly. Go back through hydrogen, nitrogen, oxygen, and chlorine and spread out their electrons as well. You done? Do you see that it doesn't change anything? Guys, there is no way to spread out one electron. You can't do it. But imagine this. Imagine that you wanted to spread these electrons out. Well, guys, if you spread them out, let's take one of them away and spread it out. Well, where's it going to go? In one of those 3 places, and it just creates another pair. So guys, understand that in the rest of these elements, spreading out their electrons doesn't functionally change anything because breaking a pair just creates a new pair somewhere else. The only place where that makes a difference is with carbon and the elements in that group. David, go ahead. It is only the group where carbon's at, but check this out. What if we did something like aluminum? So if we have aluminum with 3 valence electrons, we can spread those out, right? So why don't we talk about it? And the answer is this. Look at where aluminum is. Aluminum is on the left-hand side of the stair step, and aluminum is a metal. As a result, it doesn't belong in this conversation because metals form salts, not molecules. And so all of these elements could spread out their electrons, but we don't worry about it because they don't form molecules, so they're not part of the conversation. Is that okay? Yeah, is that?
What about stuff like
Antimony? Yeah, so if we were to draw the Lewis dot structure for antimony, it's exactly the same as nitrogen. And again, you can't spread them out anymore because you just create new pairs. Is that okay? You guys good with me right here? Okay, you're going to thank me for this later. But guys, right now, you don't even know the difference. So here's the deal. When you get to college, if you take a chemistry class in college, let me show you what your chemistry professors, many of them, especially if they're older, let me show you what they're going to teach you in terms of how to draw these structures. Guys, don't write any of this down. Just trust me and watch. But then, guys, what I'm going to show you is a way that makes these way easier, and you'll remember this, and it's going to make your college chemistry classes easier. So guys, what we're going to do now is this. We're going to take these Lewis dot structures and we're going to fit them together like puzzle pieces. So here's how this goes. Oh, shoot. Here's how this goes. What we're going to do is we're going to start with something familiar like oxygen. So guys, how many bonding sites does oxygen have? 2. So here we've got a hydrogen atom. How many bonding sites does hydrogen have? 1, and this bonding site and that bonding site literally locked together, and we just created a covalent bond. But guys, you'll notice there's another bonding site. So in comes another hydrogen, and that forms another covalent bond, and we end up with our good friend water. Here's the difference. Guys, we are not going to draw these bonds like this. We are actually going to replace them, just a second, with lines. But guys, realize that these lines represent 2 electrons shared together. Go ahead. That's exactly why. Yeah. So water molecules actually look like this. And the reason that they look like this is actually because these unshared pairs of electrons right here push on these bonds and cause the molecule to bend. So that's what actually is going on is this unshared pair and this unshared pair bend these down, and it causes the molecule to be bent. We actually call it bent, and we're going to talk about that later. So guys, this then brings up a new term. I don't think you need to write it down, but guys, notice we've got 2 bonds and then we've got 2 unbonded pairs of electrons. Guys, you need to know these terms, but I don't think you need to write it down. So guys, the electrons electrons that are involved in bonding we call bonding or shared pairs. And then, guys, the electrons, as David got us thinking, that are not involved in bonding are what we call lone or non-bonding pairs of electrons. You can call them either one. But, guys, here's the trick. When you learn to do these in college, many of your college professors are going to teach you to do it like this. Draw the Lewis dot structures of the atoms, fit them together with puzzle pieces. Guys, there's a way easier way to do this. There's a way easier way to do this. So regardless of what your college professors are telling you, ignore them and do it this way because it always works and it's easier. So guys, what is this way? Well, guys, it comes down to a collection of shortcuts. I'm going to encourage you to write them down. And then, guys, once you've got these shortcuts, we're going to do 4 examples, and then I'm going to turn you loose on your homework. So, guys, what are the shortcuts? Well, they go like this. We're going to call them helpful hints and steps. So, guys, when you're drawing Lewis dot structures, get in this rhythm. Step number 1 is put all the atoms on the paper and single bond them together. Put all the atoms on the paper and single bond them together. Now, guys, when you do this, there are some important rules to follow. Rule number 1 is this: make them symmetrical. If you don't know what symmetrical means, it means same on both sides. So when you're putting them on the paper, make them symmetrical. We live in a world that tends towards symmetry, which is actually kind of miraculous if you think about it. But guys, let me show you an example. If this isn't making sense, don't write this down. So imagine if we're doing the molecule NO2. Again, you're not writing this down. There's 2 ways we could do this. We could do it like this, NOO, but that's not symmetrical. So the way to do this would be ONO, and that is therefore a symmetrical molecule. So guys, when we're doing things like NO2, we want to go with symmetry rather than something that's not symmetrical. Yeah? Well, so you'll see. We'll still do that symmetrically, and then we're going to dig into it even more deeply next Monday, and we're really going to talk about what it looks like. But actually, NO3, I think, is even one of the examples we're going to do. So you'll see. All right, then guys, this. Carbon loves to be in the middle. If you've got carbon, put it in the middle. Why is carbon in the middle? How many, do you know? Yeah. What allows it to do that? So it changes and spreads out, and when it changes and spreads out, how many bonding sites does it have? 4. Guys, that's the maximum. Think about that. Carbon has the maximum number of bonding sites. So if you're trying to build really complicated things like living things, you want the foundation of those to be molecules, atoms that can create really complex molecules. So guys, carbon meets that criteria. So either God is really smart or our universe evolved, our planet evolved in a really logical way. But guys, the bottom line is we're carbon-based life because carbon has a maximum number of bonding sites, and as a result, it creates the most complicated molecules. Then guys, third, hydrogen and halogens can never be in the middle. Hydrogen and the halogens can never be in the middle. Guys, let's talk about why. Hydrogen is over here. If you need to look up in your notes, you can. How many bonding sites does hydrogen have? 1. Now do this. Where are the halogens? You should know it's group 7. Chlorine is an example. Look up in your notes. How many bonding sites does chlorine have? 1. Guys, that's why hydrogen and the halogens can never be in the middle. If you are a person that's missing an arm and you get together with a bunch of friends to create a human chain, if you're missing an arm, you can't be in the middle of the chain. You got to be on the end. All right? It's kind of a weird analogy. But guys, it's really the case. If you've only got one place to create a bond, you've got to be on the end of the molecule because you can't link hands in more than one direction. So guys, hydrogen and the halogens can never be in the middle. Going on from there, many times you'll see that the order that these molecules bond is actually given in the formula for the molecule. Okay, so that's step one. Now guys, step two. Step two is to count all the valence electrons for every atom. But watch out for ions. And that'll make more sense in a minute. Then guys, step three. Step three is to spread all the unused electrons around the molecule evenly. But when you do this, fill the halogens first. We've already established that halogens can only form one bond. That means their other 7 electrons have got to be in place for them to be full and happy. Then guys, one more step. Then we're going to practice on a few and then we're done. Step 4. Finally this. Check and fill octets by creating multiple bonds. Check and fill octets by creating multiple bonds. So guys, there you have it. When you get to college and your professors try to get you to do this differently, don't. This always works. But let me show you how this works. Guys, we're going to do 4 examples together. I'd strongly encourage you to write them down with me. But guys, I mean, the choice is yours. But in order to be successful with these, there's 2 things you want to do. Write big and write in pencil. Understand, guys, if you choose against either one of these, and when you find that you're not successful with these, and when you come to get help, the first thing I'm going to say is, why are you scrunching these down really small, and why are you writing in pen? So guys, big and pencil. So here we go. We're going to do 4 of these together. I would encourage you to play along. Guys, the first thing we're going to do is NCl3. NCl3. So guys, let's go through our steps. Step number 1 is to get these, there we go. Guys, step number 1 is to get these on the paper. But when we get these on the paper, we're looking for symmetry. You'll also notice that we have chlorines, and chlorines are halogens, so where can't they be? In the middle. So what are we left with? Well, guys, we're left with nitrogen in the middle. Then, Zach, this is actually also an example of what you ask. Then, guys, we've got 3 chlorines. I'm going to go like this. 1 here, 1 here, and 1 here. Now, guys, Gracie got us thinking earlier about this idea of up and down and left and right, because that does not matter. You could have put one of the chlorines on the top. It doesn't matter. You just need 3. Okay, so guys, we have now done step 1. They're all on the paper. This is as symmetrical as we possibly can get it. We're good there. Now, guys, step 2. Count the valence electrons. So, guys, looking at our periodic table, you may remember that nitrogen's got 1, 2, 3, 4, 5. So, guys, do this with me. Write it up here. Nitrogen has got 5 valence electrons. Then, guys, what about chlorine? Well, we've already established that it's got 7, but there's 3 of them, so that leaves us with a total of 21. 3 times 7. Then, guys, what we're going to do is we're going to add those up, and that gives us 26 electrons. But now you'll notice in step 3, it talks about unused electrons. So, guys, what do each one of these lines represent? A bond with how many electrons? 2. So we've already got 6. Is that okay? 6 on the board? So we're going to subtract 6, and that leaves us with 20. So now, guys, we've got to get these 20 electrons spread evenly around the molecule. Doesn't matter where we put them. Right now it does, because we've got halogens. And guys, halogens get filled first. So we need to fill the halogens first. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So now we filled up all the halogens. But we've got 2 electrons left, and the only place they can go is on the nitrogens. So now our nitrogen is all full, and now we've done step 3. Now, guys, step 4. Step 4 is actually a mental process, but I'm going to draw it for you so that you see what we're talking about. Now, guys, what we got to do is check the octet rule. Each one of these atoms has got to have 8 electrons around it. So, guys, start on the left. Do you see that chlorine has 8 electrons around it? Is that okay? The bond counts for 2. Now, guys, do you see that this chlorine has got 8? And then, guys, this chlorine has got 8. But what about the nitrogen? Well, guys, look. The nitrogen also has 8 electrons around it. Notice that the bonds count in the count for both of the atoms. Just a second. So all of these have 8 electrons around them. And so I'm going to get rid of the circles because we really don't draw them. And guys, this is an NCl3 molecule. Yeah? They all need 8. The only one that doesn't get 8 when you've done these properly is actually hydrogen, because hydrogen can only have 1. Everything else has got to have 8 around it. Yep. And so, guys, then the last thing that we've got to do is count the number of shared and lone pairs. And, guys, we only count shared and lone pairs around the central atom. So we have 1, 2, 3 shared pairs, and we've got 1 lone pair of electrons. And that then gives us the NCl3 molecule. And if you're interested, the molecule actually looks like this. Kind of blue is nitrogen, green is the halogens, and there you go, NCl3. Guys, questions about the process? Yeah?
Why do we subtract the 6?
That's a great question. And so what we're doing, Slade, is we're moving up to this idea of spreading all the unused electrons around. So to do that, we first of all need to know how many do we have. And that's 5 and 7 times 3. But then we need to know how many have we used. And each one of these bonds represents 2. 2 times 3 is 6. So we subtracted the 6 we used. Is that okay? Brilliant question. You guys all right? Let's do another one. So guys, go over here with me. The next one we're going to do is C2H4. So guys, when we do C2H4, very first thing we're going to do is get everything on the paper. But now we've got some rules. What do we know about carbon? It has to be in the middle. So guys, we're going to go, let me switch this up. So we're going to go carbon, carbon. Now, guys, we've got hydrogens. We've got 4 hydrogens, but we need to spread them out symmetrically. So 3 and 1, 1 and 3, or 2 and 2? 2 and 2. And guys, again, up and down and left and right does not matter. You just got to go 2 and 2. 2 on this carbon and 2 on that carbon. The other thing that we could have done is this. Gone 3 and 1, but that's not symmetrical.
Like, could that top hydrogen be down?
Absolutely, yeah. No, exactly. It doesn't matter. Let me erase this really quickly. Yeah, so it doesn't matter in that sense. You could have put this one up here. You could have done up, above, and below, and not to, yeah, it doesn't matter. Up, down, left, right doesn't matter. All right, so now, guys, that's step 1. Step number 2 is count electrons. Carbon has, counting over 1, 2, 3, 4, 4 electrons times 2 is 8. Then, guys, hydrogen has 1 times 4, 4. Remember, you're just counting valence electrons. So guys, that gives us 12. Now, say this is the unused ones, right? So now the idea is each bond counts as 2. 2, 4, 6, 8, 10. So we've already used 10, so that leaves us 2. Is that okay? Perfect. So now, guys, we've got 2 electrons, and we just have to get them on the paper. But guys, here's the thing that you need to know. Don't separate them. Don't go 1 and 1. They always travel in pairs. It doesn't matter if you put it on the left or put it on the right. Just get them on the paper. So guys, we're going to do this, and that would be our carbon. Now guys, we need to check octets. Does this hydrogen have a full octet? No, but it shouldn't. Hydrogen is the only exception to the octet rule. 1 bond and hydrogen is done. So guys, what about this? Does this carbon have a full octet? It does. 2, 4, 6, 8. Now guys, what about this? Does this carbon have a full octet? It does not. It's only got 6. So now guys, we got a problem. That carbon on the right doesn't have 8 electrons, but we don't have any more electrons to use. So how do we give that carbon on the right 2 more electrons? And the answer is we share some more. So guys, what we're going to do is this. We're going to take these electrons right here, and we're going to get rid of them, and we're going to turn them into a second bond. Now, the carbon on the left has 8, the carbon on the right has 8, and you just made this molecule. It actually makes it a much stronger bond. Yeah, absolutely. It's funny. We just learned that in AP the other day. Yeah, so guys, and actually a shorter bond too. Stronger is shorter. So guys, this is actually what the C2H4 molecule looks like. You get the idea? Okay, so guys, we've got, we need to do shared and lone pairs. Guys, pick either carbon. You always do it on the central atom. It doesn't matter which carbon you choose. We've got 1, 2, 3, 4 shared pairs and no lone pairs, and that would be C2H4. You guys okay? We're going to do one more. All right, so clear this, jump over here. Zach, there you go. That was the one you mentioned. NO3, but guys, notice it has a -1 charge. Oh yeah. So guys, what we now have is a molecule with a charge. It's interesting. Check this out. So guys, step number 1, get it on the paper. So in order to make this symmetrical, the nitrogen is going to have to be in the middle. So guys, we're going to go nitrogen, I don't know, let's go oxygen, oxygen, oxygen. You know what? That's going to be in the way. I'm going to move it down here. Now I've got room to write electron counts. All right, so now guys, we need to count electrons. Nitrogen has got 5. Oxygen has got 6. Just dots, right? Oxygen's got 6 times 3 is 18. But now guys, here's the interesting point. What does it mean to have a -1 charge? Do we have an extra electron or are we missing an electron? Extra electron. Guys, all that means is we've got a bonus electron. Now we can add them up, and this adds up to 24. Guys, without that bonus electron, we would have an odd number of electrons, and that can't be. It's kind of a cool idea. All right, so how many do we have on the screen already? We've got 2, 4, 6. That leaves us with 18. So now, guys, we've got to spread these 18 electrons around this molecule. So we're just going to get started. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Now, guys, what if you had started by putting 2 electrons on the nitrogen? Doesn't matter. All you got to do is get them on the paper. So if you put 2 electrons on the nitrogen, that just means you're going to have an oxygen that only has 4. And it doesn't matter. You will always end up getting these right. It doesn't matter how you spread the electrons out. So now let's do the octet rule. Does this oxygen have 8? Yeah, how about that one? Yeah, how about that one? Yeah, how about the nitrogen? No. So guys, what we need to do is we need to give that nitrogen 2 more electrons. We got to create a double bond. Where do we create the double bond? Doesn't matter. You could create it with any of these 3 oxygens. You're just going to take, you're just going to take 2 electrons off and you're going to move them into the middle and hey yo, you could have done it with any of them, yeah. And actually, if you come back for AP next year, well, I probably shouldn't say this out loud because it could be confusing. What actually ends up happening is the double bond creates itself in all 3 directions simultaneously, but that's a whole nother. You kind of do. But it's a mess. Yeah. So guys, let me show you then what this would look like. 1, 2, 3. Where's a nitrogen with 4 holes? Oh, right there. All right. So guys, this molecule then, and Cole made the interesting point, it doesn't matter where you put the double bond, and it literally doesn't. Because guys, that double bond could be down, it could be left, it could be right, it doesn't matter, it looks like this. You guys good? Okay. So, guys, I'm going to there's one more that I was considering skipping, but I think it's going to be a mistake. We're going to do it. We got one more. It'll go fast. But before we do, let's do shared and lone pairs. Central atom, how many shared pairs? 1, 2, 3, 4. And then, guys, there's no unbonded electrons on the nitrogen, so that would be 0 lone pairs. Guys, let's do this. Would you trust me enough to not write down the next one and just let me do it quickly? There's one more thing I want to show you. I was considering skipping it, but guys, just trust me on this. Carbon monoxide, horrible, clear, colorless, deadly gas. But guys, carbon monoxide does something a little bit interesting that I want to show you. So carbon monoxide starts out with C and O. Carbon's got 4, oxygen's got 6. That's a total of 10. There's 2 on the board, so that leaves us with 8. Is that okay? So what are we going to do with these 8 electrons? Well, we're going to spread them out evenly. So we're going to go 1, 2, 3, 4, 5, 6, 7, and 8. And that would then be our electrons on the board. So guys, does this have a full octet? No. How about that one? Also no. So what do? We share more. So we're going to come along and we're going to steal 2 of these electrons and put them in there. Is that oxygen now full with 8? Yeah, but what about the carbon? Still not good. So we're going to come along here and we're going to share in the other direction, and now they all have 8. And so guys, the carbon monoxide molecule actually looks like that. 3. 3 is and that's actually, Cole, exactly why I wanted to do this, is because I wanted to talk with you about the limit. The limit is 3. Oh, there we go. Here's a triple drilled one. And so guys, this thing actually then looks like this, and it is in fact a triple bond. So, all right, you guys good? All right. So guys, we are now going to dig into assignment number 3, I think, in your homework. Let me make sure, because Miss Call and I mucked up the assignments when we were thinking we were going to skip some of this. Yes. Guys, we are now doing assignment number 3. So, here's the way this is going to go. Guys, all the answers are on the wall. All the answers are online. You now have 20 minutes to work on these. Guys, no excuses, no distractions, none of that. Guys, you should get at least a third of this done before you leave today. So guys, dig in, get going on these. When you get frustrated and stuck, go back to the steps. But guys, we're going to invest the next 20 minutes in getting these figured out. Go get them.